Hi, my name is Jack and this is my physics lab 2. So to introduce lab, the purpose is to compare the actual projectile motion of a paper ball with two models. And the models used are glow script, and the principles used are Newton's second law and the drag equation. The system is a paper ball and the surroundings or sources are the earth and the air. Here's the video of the experiment. And below is the Newton's second law. So the observation is the paper ball had constant velocity in the x direction while gaining velocity in the y direction, then velocity decreased in the y direction, which is the sort of parabolic shape you see here. And this is due to the force of gravity. And there are some bumps in the graph, could be due to human error, imperfect throw, etc. So the model used was glow script, and it was used to make a model of projectile motion with and without drag. So on the left is the no drag, and the right is the drag. You have to assume that the initial velocity is the starting velocity of the tracker video. The mass is 0.0016 kilograms, and the starting position is that of tracker. For no drag, only Newton's second law was used, so no drag equation. And then for drag, use that Newton's law equation and drag as well. And the constant was 0.0002, and the time step was 0.001 seconds up to 0.6 seconds. And so the graphs are pretty similar, aside from a couple differences, like these two are a little different and these two are a little different. So here's the code. The top is really just initializing, setting the mass, setting the position, and the velocity, and the time, and the g constant. Bottom left is no drag, so you don't have that equation for drag included in the net force. Bottom right is the drag, so you have the force of gravity, and then you have the force of drag equation, which is taking the magnitude of the velocity times a constant, times, then you square the velocity, and then you multiply it by the normalization of the velocity. And then you add those two together to get the force of drag. And those are the while loops. So the comparison, here are the scatter plots. You have the actual movement from tracker, which is the blue, the green movement, which is the drag trajectory, and the orange movement, which is the no drag trajectory. So you can see the no drag sort of moves farther out in the x direction and higher up in the y direction because there's nothing to bring it down. The initial trajectory starts out the same for all three, but the maximum heights are different. Obviously, the one with no drag travels higher and farther out. And there's a little bit of difference from the drag in the tracker, but that could once again be because of imperfections. So what if the ball was only thrown straight up with the same initial velocity, it would take longer to land than if it was thrown in a parabolic direction. And this is because the ball thrown straight up has a larger initial vertical velocity than if it's thrown in a parabolic direction. And also assuming drag acts on an object moving in both directions in those both directions. So since it's acting in multiple directions, the drag force would be greater. So if you add, let's say, a z direction as well, then the drag force would have to act on that as well and be greater. So the drag would be larger in the parabolic situation, bringing the object down to land earlier. So what does it mean? Neither model predicts terminal velocity because there's at least one direction for either where the velocity is not constant. So as you can see in those graphs before, the x velocity isn't constant. The x and y velocity aren't constant for the no drag, and then the y velocity isn't constant, or the x and y velocity aren't constant for the drag, and the y velocity isn't constant for the no drag models. A similar experiment to design would be something that has to add to the drag, so it's equal to the force of gravity. So then as you can see in the equation, if net force equals 0, drag minus gravity has to equal 0, so they have to be equal. And using a projectile with more surface area, or one with more material that creates more air resistance, will help the object reach terminal velocity. So to conclude, there will always be some force of drag acting on a projectile unless in a vacuum, which is not realistic. The velocity of a projectile may reach terminal velocity if there's drag, but the drag has to cancel out the gravity, and this isn't too common. As you can see, it didn't happen in our simulation. And the parabolic projectile motion has drag acting in both directions, meaning the larger drag force in a single direction. And then the only other force is that of gravity. Hope you enjoyed.